I just want to let everyone know that I'm recording the whole session. Hey, Pam.
Hey, Neela. Teams is behaving for me today. I hope it continues. I see you record.
Started recording, yeah.
Yeah, that's wonderful. Thank you.
Hey, Pam. Steve here.
Hey, Steve. How are you doing?
Doing well, thank you. Looks like we got a big group here.
What's up, Casey?
Hey there, Pam.
At the helm there.
Yeah, I figured I'd show my face at least before we get started, so
At least start that way.
people can visualize.
It's been so long since I've seen you. My goodness.
I know.
Jeez, it looks like he's grown a couple of feet. It's starting to look like a lumberjack out there.
I think a lot of folks are these days.
Yep, that's how we're getting our exercise. Splitting wood for the still for the rest of the winter there. Denver.
Well, our last trip out to Asheville and Boone was just about our last time I traveled. I think I might have had one more, but
I know. Who would have thought?
Seems like ages ago now.
Who would have thought? Although I did do a drought exercise for the city of Asheville last month, so I did get out once. But that's always challenging too, trying to do some of it virtually. But training is a whole different matter.
Yeah.
So
yeah, it's too bad. It is the one that really does not do well with remote.
No, I can't supervise while Casey's instructing. So this is a demo.
Right.
More than anything else.
Yeah, who knows? Maybe down the road,
right.
Pull something together for multiple models or something. But still a ways off probably from logistics there.
Yeah, pretty far down on the vaccine list. Just, that's fine.
Yep.
Luckily for me, it's very easy for the most part to work from home, and I have kids, so it's very doable. Let's see here.
So, do you have any idea, Pam, about who you're expecting? How many? You have a decent crowd so far.
About 20 in so far. I think we'll give it till 1:05. Give people a couple minutes to come in after lunch. Hopefully, everyone's got a coffee and a sweet. keep the energy going. Normally, we would provide that at this event. Sorry about that.
Pam, should we start adding our names in the chat so that we can have record of who is attending?
Yeah, thanks for the reminder on that, Neela. Yeah, if your name isn't clear as you've signed in, if you could just put in the chat box your name and what organization you're with, that way we have a nice record of who all was able to attend today.
Casey, just don't start jumping up and down with excitement because you're going to hit your head on that light bulb.
I know it's
Oh my gosh.
I'm on my I'm standing.
Okay.
I'm used to doing these at the podium, so I'm on my standing desk here.
I love it.
This fan's on the list in the place of our house. It's from the 80s or something, but
if Casey if he can't answer a question, we'll flick the light on here.
yep, exactly.
All right, let's see how many more have joined here. All right, we're at 22 now. It's already 1:05. I think we can probably go ahead and get started. And again, welcome everyone to this demonstration of the Yadkin PD and Lumber OASIS model. We do have Steve Nebeker and Casey Caldwell here to run through what was prepared for the Yadkin PD and Lumber River basins. And we originally intended to wrap this up at the end of 2020. Given everything that happened, I'm pretty impressed that it's only 3 weeks later that we're getting to do this kind of big final step here. We could talk about what happens next at the end of the training, but I just wanted to say hi to everyone before I pass it over. And again, if you wouldn't mind, in the chat box, just writing your name and organization. That's our new electronic sign-in sheet method, if you don't mind. Pretty much just see myself in there at this point. All right, so at that point, Casey, are you taking over here?
Yeah, I'm gonna run the show today, and Steve's gonna help pitch in where needed. So yeah, I guess we'll get going, and I think Steve can help watch the chat for me. I think the chat should pop up, but if it's blocked by a window or something, Steve can funnel questions to me. But thinking maybe if folks want to go on mute, and then if you have a question, obviously chime in anytime. As Pam mentioned, obviously ideally this would be done in person. I think at least a handful of you were here we did 2 trainings last winter for the French Broad and the New and Watauga River Basin models. And those were in person, and we, had, a half a dozen instances of the model up, and people kind of went in groups and were able to follow along. As you can imagine, virtually that's a bit hard to do that. So essentially what I'm going to do today is a demonstration, and I'm going to turn off my camera so you don't have to look at me anymore and share my screen. And so the demonstration is going to introduce the model. I'm going to walk through kind of where to find a lot of the stuff, how to navigate the model, how to find input data, how to make changes, how to view output data. We'll do a couple scenarios so you can get an idea of how to start to craft alternative scenarios that I know the management group is interested in using the model for. And I'm also going to demonstrate how to update the inflows, at least the provisional inflow record, which we've talked about previously. I'll explain a little bit as we're doing that, and how to run a forecast and position analysis for the model. I think we have 3 hours blocked. I don't think we're going to go longer than 2. If this was interactive in person, I think we could bear through that. But I think 3 hours of me just talking on my screen is going to be more than we need. So I think we can do it in 2, but we have plenty of times for discussion. So if you need me to repeat something, or if you have a question, just chime right in. don't worry about waiting until the end. So as I mentioned, this is kind of going to be more of a demonstration, a tutorial. We are going to provide, once the model's up on a server, we have a series of tutorial slides that more or less are going to follow a lot of what I've done today. And so those will be available to all you as a refresher once you do get live access to the model, but also if there's any new folks in your organization or in the stakeholder group that want to jump in. These are pretty straightforward, just kind of click through how to do lots of stuff. So hopefully kind of really step-by-step, click by click. So that will be the companion piece to today's demonstration. And there is a user manual for OASIS. A good chunk of the user manual is outdated because it's based on the classic version of OASIS that DWR had used up to date. So that's things like the interface, the graphical user interface is not current in the user manual. However, everything pertaining to OCL, which is the coding language behind OASIS, and the post-processing scripting, that's all still current. We haven't changed anything in terms of how the model runs. So if folks are getting into doing a lot of scenarios and actually writing OCL and everything, the user manual actually still is a great reference for that. And so that will be on the server as well, and people can reference that. So there's this section here is all syntax of the OCL and everything. So that's still relevant in that aspect. And with that, I'm going to get going. We're still working with DWR. I think Pam mentioned we'll talk next steps, but the model will be hosted on a DWR server. We're still working on helping them get that set up. I'd imagine it's going to look something like this, where you click in and you can either open a desktop, a remote desktop, or I think we'll have the ability to directly open the model itself kind of in a standalone window. And for those of you familiar with using the model with DWR in the past, you might have had accounts for various models. Let's say you had a client or that had a Cape Fear model and a TAR model or something. So whatever models you have accounts for, you're going to have shortcuts for those different models. So for now, I'm just showing this YPDL, Yadkin PD Lumber OASIS model shortcut. And so once you log into the remote desktop through the server, you'll just open it up there. And that's just going to load. And so, okay, so now we have OASIS open. So this is the graphical user interface from OASIS. It's how everybody's going to interface with the model. By default, the model is just going to open up in this tab called Find Runs. So that's probably pretty self-explanatory. That's where we're going to find runs. That's a good starting point. We can also find lots of other stuff. I'm going to go through a lot of these tabs up here. OASIS has a bunch of tabs to find data and runs. Once you have a run open, there's a lot of options in terms of runs and input data. And then we'll talk about post-processing in terms of plot. And then there's some other pieces that tie into other parts of the demonstration. So if I'm in my Find Runs tab, I can search by a number of parameters. So this is going to be useful on the server. You can see here I can search by username. So someone wants to go and double check Pam's runs, they can do that, or my runs. But I'm going to close that parameter for now, so I can add or subtract parameters this way using these control buttons. And all I want to do for now is search for a run by name. So if I pull this first drop-down menu, I can just search by run name. There's a lot of qualifiers there, but I just want a run that is named Symbase, because Symbase is generally what we call our base case scenario. There's a couple there that are older, but what I'm really, and obviously there's just going to essentially be a handful of runs on the server once it's set up. There'll be Symbase, there'll be POSBase, which I'll get into is the forecast-based run. And then there's we're gonna work with DWR once they have the model to set up the various demand year runs. So Symbase is based on the most recent current data in terms of demands and operations in the basin. And then based on the projections from the local water supply plans, we'll have future demand scenario runs, I think in 10-year increments. I believe that's what we've done with the other models out to, what's our planning horizon at this point, Neela? I'm not started doing these so long ago, I can't remember.
It's 10 years.
10 years and then probably out to what, like 2060 or 70 at this point?
50 years projection.
50 years, so 2070. Okay. So once we have the model up in the server, you would see a number of runs with all those different demand years. I'm just going to start with SimBase. So again, this is our simulation of current basin conditions based on all the data collected that was detailed in meetings last year. And when I look at this list of runs, there is a number of things that kind of describe what's going on. Name of the run mode, simulation, the user that created it, when it might have been modified, if it has been executed or run, it tells when that's happened. There's that checkbox. And then there's also this lock. So the base runs that are going to be provided to the DWR will all be locked. So they can't be modified by any user. That's kind of a quality control feature. But any run can be viewed. So you can view the inputs and outputs of any run, even if it's locked. And you can make a copy of that run, which I'll do in a couple minutes, to create your own scenarios. So that way, nobody can go in and by accidentally change something in the base run. So everybody's working off the same base run. This date expires. That's something we have set up right now on our development server. I believe we'll set these runs to not expire. So don't worry about that. Okay. What I will do is show you how to copy a run right now, just so we kind of have a run to work off of. And so if I have a run selected, I can really just click anywhere in this row. I can also click all the way to the left of the row to highlight the whole thing. Doesn't matter. As long as I have the row highlighted, I press copy. So under the run tab, I press copy, and I'm going to get this new dialog box. And there's a number of options here. So I can put in my new run name. I could just call this test one. So that can be, a good rule of thumb is to have descriptive run names. If you just have 1, 2, 3, 4, 5, you might forget what you did. It's good to have some description of what you're doing with this scenario in the run. But then you also have the ability to write a description if you want. So this is where you can put some more detail on, like, in this scenario, I changed blah, blah, blah. And so then if somebody goes and looks, or if you need to remember what you did a year ago, you can pretty quickly see your notes there. All right. From here, I can open the run in a number of different ways. I'm going to open it in what I'm calling the setup window. If anybody's on the phone who used the classic OASIS, this is pretty similar to the setup tab that would have been in classic OASIS. So it just has a number of things that user might want to look at or change at the beginning of a run. It has the start and stop date of the simulation. Our simulation can go through, we can actually go sooner, or we can actually go through whenever the inflows are updated. Right now I have it running through the end of 2019, and I could change that. It starts on October 1st, 1929. That's when our inflow data set starts. That's been detailed previously. And I'll mention, in addition to the tutorial and user manual, there is going to be a report that will be delivered with the model, detailing the model development, including the inflow development and data development. So that's stuff that might not be right in the model in terms of how things were developed. There's a table here called OCL constants. These are just a few things, not many, that the user might want to change for the run. We kept this pretty clean, sparse for this model. Most stuff is set in the OCL or the schematic. Really, the only things to worry about are this drought plans on switch So we have all the drought plans that could be coded for all the entities, and then also the low impact or the low and flow protocol coded in this model. And so what you can do actually is run the model with all those on or off. By default, they're all on, have this switch to 1, but you click that, switch it to 0. We also have a demand multiplier in the model. This is something we added to DWR's models a number of years ago, and it allowed them to do kind of system-wide sensitivity analysis. So if you turn this demand multiplier on, and I'm going to do a demo of this later, but if you turn the multiplier on by switching this to 1, and then you enter a value here, let's say you wanted 1.25, what that is going to do is increase all basin demands by 25%. So it's obviously not the same as your discrete 10-year demand projections that are actually based on the projections from everybody's water supply plans. But if you just want to do a rough analysis, sensitivity analysis on what if demands increase by a certain amount, that's a nice way to do it. And then I can just turn it off there. The next table, initial reservoir storages. This is just my starting storage for each reservoir that's in the model. So you can see there's a long list of reservoirs. A lot of reservoirs we're capturing the model, not just the main stem projects. And you can see that we specify a starting. So this is literally just at the beginning of October 1st, 1929. In this case, this is what my storage or elevation starting out for each reservoir. This becomes more important if you're doing a forecast run, because a forecast run is an analysis of where things are heading depending on today's starting storages. But obviously, if you're doing like a yield run or something, you want to make sure your starting storages are at the appropriate volume. And then the last piece here is a list of OCL codes. I alluded to this earlier, but a lot of the operations in the model are handled through things that will show in the schematic, but then some of the more complex operations like the low and flow protocol, the drought plans, allocating sales and purchases, interconnections, things like that are all done in OCL code, operations control language. So I'll show that in a little bit as well, how to access those and how to read them, modify them. Probably what a lot of users want to start with though, and I could have done this when I opened the run, but I can do it from here, is to take a look at this schematic. So I'm going to click on the schematic button here under the run tab. That's just going to take a second to open. Sometimes it takes a couple seconds to open stuff, move around in this model. It's one of the bigger models we've actually built, as you'll start to appreciate from the schematic. We've captured a lot of complexity in this basin. So it opens the schematic. It's kind of zoomed into a middle portion of the basin here, but if I look at the lower left here, this is a navigation pane of the entire basin. So if I click within, I have this little pink rectangle shows where I currently am. If I click and drag that, it's gonna navigate me around. So I can go all the way, down to the Waccamaw, all the way up to Karscott up here. And then I can zoom in and out a number of ways. You obviously can't see, but if I, just hold down Control and roll my mouse wheel, I'm zooming out. I can zoom in the same way as well. If you're on your laptop, obviously just the zoom in and out features on your trackpad will work. I can also just zoom in on discrete points. If I click the zoom button, I can just zoom right in on Karscott there if I wanted to. If I click the pan icon, I can move around manually. Okay, and then there's also the ability there's this zoom button here, so I can zoom to fit. That's going to zoom to the whole basin. If I want to zoom out, reset zoom, zoom in, zoom out. So pretty easy to move around. If you're familiar with the old model, the schematic was not quite as easy to navigate. So let's go over what all these different nodes and arcs represent. So if I just zoom in on the legend quickly here, The red triangles are reservoirs, or we also have one natural lake, I guess, in this model, technically, Lake Waccamaw. The blue squares are demands in the model. That's mostly municipal industrial demands and also some agricultural demands. The yellow ovals are just junctions. So that's just a point of interest in the model that doesn't include some of the other categories we have here. The green ovals are USGS gauges. So we have, I want to say 35 USGS gauges. Does that sound right, Steve? In the model, maybe a little more, where we develop the inflows for, and we can zoom in on some of those there. The light blue ovals are what we're calling total withdrawals. So as I mentioned, we're capturing interconnections in this model. So maybe if I zoom in, where should I zoom in? Somewhere a little less cluttered, but this is a good example up here. I go to up here in the way upper basin, we have Mount Airy, we have Dobson. So the light blue oval, it represents Mount Airy's total withdrawal. So Mount Airy has two intakes, two reservoirs here. The green arrows represent the withdrawals from those water supply sources to their system. The light blue arrow represents the portion of that withdrawal that goes to their actual system demand, represented by the blue square. And then the dark blue arrow in this case, you can see is actually going to Dobson. And that's because Dobson buys water from Mount Airy. So that's that portion. So not only are we tracking the surface water withdrawals, we're also tracking where that water goes in the system. So some of it goes to Mount Airy, some of it goes to Dobson. So that gives, that way we have the ability, let's say that management group is doing some scenarios and they know that that purchase is going to increase or decrease in the future, they can set that in the model and not have to worry about, and then that in turn is going to decrease Dobson's own raw water withdrawal from the Fisher River in this case. So there's a lot of, and I'll show where some of that's set, but so there's a lot of detail in the model in terms of where water is moving around. If I go back to my, back to my legend. So that's total withdrawals. So for entities that are moving water, basically sending water not just to their own demand, we have these total withdrawal nodes. So you can track their total withdrawal and where it goes from then. We also have the brown ovals represent wastewater treatment plants. We have two types essentially of wastewater discharges. Generally, where there's going to be an actual node, that is a wastewater treatment plant that's not linked to a demand node in the model. It might either, in the case of maybe, High Point or Union County, it's where water is coming from outside the basin, being discharged into the basin. Or if it's an entity that maybe is only on groundwater, and then they have a discharge, we're representing it there. The last type of node is time of travel. We only have two time of travel nodes. In consulting with the technical review committee, we determined that really the two important places to account for time of travel is the time that it takes for releases from Scott to get down to High Rock and Yadkin College, because that does impact High Rock operations, especially when high flows are concerned. So we're lagging flows by a day down there. And then at the bottom of the basin, we are lagging flows, I believe, by 2 days, where the water leaves the state and then eventually ends up at the PD gauge down in South Carolina. So that will help us, as the management group I know is looking at certain impacts to South Carolina flows. So that will help. That helps with quantifying the flows down at that PD gauge further down in South Carolina. Other than that, we have so many inflows in the model. We've captured so many intervening gauge flows and incremental inflows that all those kind of account for incremental inflow. So we're not talking about huge amounts of water needing to be lagged in between. And then I'm going to move on to arcs. So there are a number of different types of arcs in the model. The black arcs are just regular flow. The flow is in the direction of the arrow. The light green arcs are representative of surface water withdrawals. So wherever you see a light green arc, that's water being actually withdrawn from a lake or a river intake. The light blue arrows represent the withdrawal to a demand node. So again, if a system maybe has multiple intakes and they're selling water, the portion of water that actually goes to their demand node is that light blue. And then we have two types of interconnection arcs. The dark blue represents regular interconnections. So, an interconnection that's made, I forgot what I think it's a number of days criteria in the local water supply plans, maybe 30 or 60 days, more than that a year. So if they're making a regular sale or purchase, that's included as regular. And then an emergency interconnection, we've plumbed a lot of those that were included on the local water supply plans, but those generally they're not turned on by default in the model. Those are more there if for alternatives analysis, if an entity wants to take a look at, hey, what if in our 50-year projection, what if we're thinking about turning that emergency interconnection into a regular one, or maybe we write it into our drought plan as something like, if we hit stage 3 of our drought plan, we buy 5 MGD or something. So that's where those could be used potentially in alternatives analysis. There are a number of purple arrows that you can see, and these are always just kind of the purple arrows they're not connected to anything on one end, and then they always are leading to a node. Those represents all the points where we have natural inflows into the model. So anytime we have a USGS gauge, so here's, for instance, the South Yadkin near Moxville gauge, we're going to have an inflow there. But then additionally, in this case, Statesville has a intake, although they're not really using it as much these days. They get water from the Catawba now. We'll have incremental inflows also at any points that are important, like an intake. And then also reservoirs, we have inflows. So what these represent are incremental natural inflows. So the purple arrow on High Rock isn't the total natural inflow to High Rock, it's the incremental inflow, less the inflows upstream. And the inflow methodology kind of details how all that's chopped up. The other two types of arrows, there's these brown arrows, and then these kind of light orange yellow arrows. And those are both related to wastewater discharge permits. The dark brown are, again, wastewater treatment plants. So those either come from these, what we call independent wastewater discharges, like you can see here. And then they also come from if we have wastewater that is linked to a demand. So, Albemarle, for example, has their wastewater treatment plant that discharges, I believe, kind of upstream of a tributary to Big Bear Creek. So that arrow here represents that discharge. It's coming from the demand node and it's going into the system. And there's a couple cases where we have regional wastewater treatment plants, WSACC being one of them. So you can see here we have a wastewater treatment plant node, and it has wastewater from 3 different demands feeding into it: Kannapolis, Concord, Mount Pleasant. It also has it's a little hard to see, but a little inflow arrow here that's brown. That represents additional wastewater from entities that aren't here. There's a couple communities that aren't surface water withdrawers, but they do contribute to WSACC's wastewater. And then from that treatment plant node, the discharge is coming into the river. So we have, I think, WSACC, I think there's Yadkin, up on the upper Yadkin, there's a regional plant, for Jonesville and Elkin. And there's also a regional plant, Anson County has a regional plant down here. So a few of those. And then the last type of arrow is this orange arc. That represents, it's also tied to an MPDS permit, but in this case, it's a water treatment plant discharge. So if a water treatment plant process discharge had enough discharge above our 0.1 MGD threshold, we included it as well. Now you can notice as I'm navigating around, all the demands not only have a name, they also have their public water system ID number right there. And then if I were to double click on a arrow, so I can click on any demand, any node, and any arc. So all I'm doing here is double clicking on Norwood's wastewater treatment plant, and you can see there it has the permit number there. So you can keep track of permit numbers that we're tying all these to. And then if a wastewater treatment plant is just an independent node, it's got the MPDS permit number right there. Okay. And then additionally, we have gauges labeled with their gauge numbers, so folks can easily reference those. Okay. So I think just to do a quick, to show you how to pull up data in the model from the schematic, I'll start with something easy. I'll go to Karscott Reservoir. I'll double click on it. So if I double click on a reservoir, it brings up a little dialog box here that shows me a bunch of information. Folks might be, and I'm going to show how to modify these, but just to show how to view it quickly. Let's say I want to view my stage storage area table. It shows here I do have a curve. And what I can actually do, if I hover above the left corner, a little dialog box will pop up and it says, click to open this import source in a new plot window. So if I click that, a window is going to open here. And what it does, it shows my stage storage area curve. It shows the values here, and then it shows it plotted here. And I also have a number of things that I can view right from the window. I can view my rule curves. If a reservoir does have rule curves, which a number of these do. It says my inflow source is OCL. I'll show that a little later. It shows my dead storage value. Right now, it's just set by a constant. So whatever I'm putting in here, you know, I could have that be defined by a pattern or OCL as well. Initial storage is going to match whatever I changed in that setup tab I showed before. And then you notice here, I have flexibility on how I want to represent any of these values. So let's say I wanted to work in acre feet or millions of gallons instead of feet, I could do that. The weight table over here, the weights are the way, or one of the ways that OASIS decides how to allocate water. Reservoirs have a number of zones. The A zone is anything at or below dead storage. The B weight is whatever's below my lower rule curve that I've defined. The C weight is generally the conservation zone. It's going to be in between the upper and lower rule curves. And then the D weight is usually reserved for flood storage. It's whatever's above the upper rule curve, but below my maximum storage. Sometimes we're not modeling flood zones, but in the case of something like Karscott, we are. And then the weights themselves, the numbers, the absolute numbers aren't important. Weights are all treated relatively within the model. So the simple way to think about it is, you know, something with a higher weight has the higher priority. So if Karscott conservation zone has a weight of 1250, and then I go and double click on Karscott's min release, which is this arc right here, you notice that has a weight in something we're calling the A zone of 1500. That represents the minimum flow priority. So since 1500 is greater than 1250, Karscott's going to prioritize meeting whatever minimum release we define instead of holding it in storage up to the minimum release amount. Okay. You know, the weights are all set up in this model according to the operations for the base case run. The only time you need to worry about them is if you're really going in and modifying a scenario. Let's say you're adding a new demand or you're adding a new min release or something, then you're going to have to make sure you think about how the weights. So the last piece is, you know, demands also have a weight. So you notice in this case, I just double clicked on Wilkesboro demand node. It has a weight of 1,000. So Wilkesboro, which draws water from the river downstream of Carscott, releases are not explicitly made from Carscott to meet Wilkesboro demand. The minimum release essentially was built to factor in Wilkesboro's demand. That's the way they kind of negotiated, I believe. But if for some reason somebody increased Wilkesboro's demand to 100 MGD, it's not going to drain Carscott because of the way we have the weight set up. Okay. Let's do. Go ahead.
So well, the beauty of the weighting system is that we can avoid writing a lot of code, which would involve a lot of if-then statements. So it greatly condenses the amount of code that you have to put in there.
Yes.
And you may talk about targets where the user specifies some action that is of importance. One of them is from Carscott that, say, for Wilkesboro and Winston-Salem, Winston-Salem, they can call for additional water above and beyond the minimum release.
Mm-hmm.
It flows in the river, and the associated demands hit certain levels.
Yep.
So.
Yeah. Well, and that's where you get into OCL. But like Steve said, one nice thing about building a basin model this large is we don't have to explicitly have code for every one of these demands. So Yadkinville, for example, it's a pretty simple system. It's got one intake. It's got pretty new reservoir upstream where they can meet their demand from. And so we don't have a block of code in the model that says the release from 5D reservoir has to equal, the demand for that day for Yadkinville. And then if there was a min flow plus that or whatever. If I just quickly open up 5D reservoir, it has a weight of 1250 on the storage. And then if I look at Yadkinville, it has a weight of 1500 on demand. So OASIS is automatically, when I run the model, gonna make sure to release water to meet Yadkinville's demand. Less maybe the intervening inflow in between. And so there's no manual writing of any of those calculations. It's done automatically once you have the weight set up properly.
And this is all done through a linear program, which has if some of you remember your, well, I'm sure a few of you have taken classes in linear programming, but you're trying to maximize an objective function. So the objective here is, for the most part, maximize the water supply delivery and subject to constraints on, or let's just say minimum flows could be arguably treated as constraints. And then the linear program will use those weights, multiply those by the flows in the storage to try to maximize the overall objective function.
Yep. And that's all I can show how to access. If folks want to dig into the guts of the model, all that can be surfaced. Generally, that's not necessary or desired because it's a lot easier to verify stuff's working through some simple output techniques where you don't have to dig into the linear program. But it's important to point out what is going on kind of behind the scenes. It's a systems model, so essentially every day, since this is a daily model, the whole system's being solved subject to those goals and constraints that Steve mentioned.
So it is an optimization tool. Every day, OASIS is figuring out the best way to allocate that water, but the priorities are really stipulated by the user.
Yep.
And each time step, OASIS will figure out how to move the water based on those priorities. A pure optimization would be more along the lines of hydropower, where if you were to put in, for instance, prices by hour, OASIS would try in this case, to maximize hydropower revenue, subject to all the constraints on minimum flows and lake levels, that kind of thing. We're not doing that with this model, but we can transition to that kind of optimization tool with if we start incorporating pricing. And that's what we did on the Roanoke River Basin, where we took the originally developed Roanoke River Basin model and then turned it into a hydropower scheduling tool, which is used by, in this case, Dominion, Virginia Power. So I know Cube is on. A couple folks from Cube are on the line. Ed Bruce is on the line for Duke. But yeah, this has a hydropower component that is right now sort of representative of overall operations, but ultimately could be refined to start looking at optimization approaches.
Yeah. Just quickly, Klaus, did you resolve getting access to the screen share? It's on the chat.
He did. I think
Okay.
it was Fred who was having trouble, but he restarted.
Oh, it was Fred. Sorry.
Yep.
Good deal. Catching up. All right.
Let's just make sure that the others are there. Like Pam, you hear us?
Yes, I can hear you, but
Okay.
I can't see. I cannot see the chat box. I don't know why. I'm not seeing any of that conversation, but that's on my end, so don't worry about it.
Yeah, sometimes you have to open Teams from the taskbar and then pull up. It's a separate window from the shared window, or if you're in the, well, obviously this looks different because I'm sharing, but there's this little icon here.
Right. Yeah. When I click on it, all I see is that I've entered my name.
Oh.
It's so weird. Yeah. So
well,
anyway,
I got the list
right.
of names, so I think we should be okay.
Yeah.
In the chat.
Yeah. Because we have Russell from Monroe, we've got Bill Brewer from Salem, so we've got some utility folks, Robert from Davidson Water.
Great.
And and then
this is a good time for others to weigh in if they have questions or any comments.
Yeah, I'm just I'm about finished up with kind of the really broad overview, and I'm going to start digging in how to change stuff and start digging deeper. So if anybody had any questions on the outset here, feel free. Otherwise, I'll keep moving, and we'll maybe take a break in 30 minutes or something if folks need it.
Well, and just I'll add something here, for those who weren't on the last call, which was a sort of a overview of the overall model development to the broader stakeholder group. The SIM-based scenario, current demands, current facilities, current operations, that's all populated with data in terms of water demands and wastewater discharges that line up with what Jonathan Williams and HDR did for the water management group, because that's really important in this case. We have so many different entities. We need to make sure that everything tracks, and we did a comparison for essentially today's conditions and made sure that there was very good agreement there. Yes.
Thanks, Steve. Well, if there's no questions right now, I know we're still kind of on the basics here. I'll keep moving. I'm going to talk a little bit about demands and how to change them. So I mentioned there's essentially three different types of demands. There's municipal, there's industrial, and there's agricultural. The municipal and industrial, I can view and change right from the schematic here if I want to. So I know we have folks from Monroe on the line. If I were to click on Monroe's demand and double click it, you get a much smaller dialog box than the reservoir. That's because it's not as much to change. So essentially the important parts are, I have a weight, so that's dictating, again, that priority when the model's solving. I have a multiplier, which represents the annual average daily demand for the system. And that's based on the average of the most recent 5 years through 2019. And then I also have a I'm defining, you can define demands in a number of ways. All the demands in terms of municipal are defined as time patterns. So essentially what that means is I'm taking an annual average demand and multiplying it by a monthly pattern. So I have, generally more demand in the summer, less in the winter. So if you missed what I did there, it's the same thing I did for the stage storage curve. And there are a few ways to access all this information. I'm just showing from the schematic, since that's, I think, a lot of users that are just focusing maybe one system or something. That's generally maybe the easiest way to do it. So again, if I hover over my little demand drop-down menu, I have the option to open this import source as a plot window. Then it opened as the plot over here. One thing that might be helpful as you're using the model is you can pin different windows in different places. So let's say I want to have this window open, but also be able to look at the schematic. If I click on this window up top here and drag it, you'll see this little menu here that pops up. So let's say I just want it pinned over to the right. I let go there. And then now I can look at my schematic and this little demand dialog box at the same time. And then I can do something like drag this over. And so one thing, it's a little confusing when the first time you see it, it says 2000. But this is really just a repeating pattern. And it just, I think the way our database stores data, it shows 2000. Maybe, I think we might have on the list to get rid of the year and stuff and just show the month and day. But so what the model does is when you run it is every day of the year, it takes this annual average demand, in this case 6.61, and depending on the month you're in, it multiplies it by this fraction. So in January, my demand's only 93% of that. And if I'm out in August, it's 1.11% of that. And again, that's based on actual reported data that we collected. So we took the most recent 5 years of data from all the utilities and figured out these patterns based on the most recent 5 years. So it's not just based on 1 year, because in any given 1 year, depending on what happened, climatologically or with your customer base, there might have been kind of month to month, something a little weird going on. But if you average it out over 5 years, you get generally a pretty reliable repeating pattern. And this graphically shows it over here. I'll show a little more on plotting window, but I can kind of drag. So if I just want to show 1 year of the repeating pattern, I can just click and get over here. So again, in January, slower, and then all the way. So it's about 6.1 or so. And actually, I can do a rollover. So if I click that little rollover button, it shows me. So in January, my demand is 6.15, and then in August, Monroe's demand peaks up to about 7.3, and that all averages out to the 6.6 annual average. So I could change the demand right there. I'm just going to close this window. If I wanted to change Monroe's demand, let's say they wanted to do a scenario where their demand jumped up to 8 MGD annual average, I could just do that and close it. And then let's just show, since this is obviously an important piece, how to run it. So if that's the only change I want to make, I go over to my Run tab. And then you'll notice there's a button here called Execute. So if I have a run open in either the Setup tab or the Schematic tab or somewhere else, I'll execute that run. What I could, if I'm back here, and I'll show this as I do some more alternatives, I could actually highlight multiple runs and run them at the same time. In this case, I'm just going to run one scenario. There are some options that come up here. By default, runs do not lock after you run them. I'd say for the uses that this group is doing, that's what you're going to want to do the majority of the time, because generally what you're doing is, developing alternatives. Maybe you run it and then check and say, oh, actually, we need to change that operation. Let's run it again. Locking runs is generally, again, we do it for those base runs, so nobody changes them. But then maybe if you're doing forecasts every week for a system, and you want a clean record of what had been done previously, then you'll have them locked by default. If I'm running multiple runs, I can do them in parallel. And then there's some other output I'm not going to show yet, but if I really want to go deep into debugging, I can activate something called the balance sheet. That's going to be an output file, and this is going to slow down the run. So generally you don't want to do it. It shows, it tracks every unit of water at every node in ARC at every time step. So that's, as you can imagine, a huge output file, but sometimes it's useful for debugging. I can also view very detailed output on the OCL results. So again, the solving of the LP itself as well. So again, choosing any of these options is going to slow down your run. You only really need to do it if you need to do some more sophisticated debugging. And then I go and execute if that's all I want to do. A little dialog box pops up. It just takes a minute to initialize. It's reading in the input. It's reading in the modules. There's a module I'll show in a minute that's being used for agricultural demands. You see it shows the start, the end that I've set, and now it's running. It shows your progress there. I can go and do other stuff with the model as this is running. So if I wanted to go and start on my next scenario, I can let this run and it will do its thing. So that's a nice feature that wasn't available in the previous version of the model. And just because the way that data is stored, and I think this will be true for the new server that DWR are setting up, because it's pretty modern processing. We found this is quite a bit faster than the old version of the model as well, and that the simulator itself is no different, but just because of the reading and writing of output files, the way it's different, we've actually sped up things a bit versus the classic version of OASIS. I think it took close to 2.5 minutes to run this version of the model in classic OASIS, and it's taken, you can see here, we're getting towards the end. It'll probably take maybe 1:30 to run the full simulation starting in 1930, going all the way through 2019. Right. And then it just takes a second to finish writing output, and then it's done. And once it's done, you can close this window. If you want to stop it, if you realize you made a mistake or you don't want to run the full record, if you click this, if you close this window before it's done, it will actually just stop the execution of the model, at whatever point you click it. But if I can just close it there. So I'll get more into output in a little bit, but just to quickly show that we can contrast what happened here, and if I go back to my search runs, I'm going to close this. I'm going to go to a fresh find runs tab. So if I go to find runs, I want to find runs by me. And then I can do something like I can highlight both test one, which I just did, and I can also highlight Symbase, which is my base case run. And then right from the run tab, I can go to this window called process plot. I'll show you how to build post-processing plots and text files, but I have a bunch pre-made, so I'm just going to show one for now. You can also search for processor codes. So a processor code is just a predefined output script, essentially, that someone's built. So because this is the development version of the model, there's a lot in here that Steve and I developed. A lot of these will be included in the final version of the model that's delivered. So there'll be a lot of output already available, but with the training, you'll also be able to develop your own output files as needed for specific systems or scenarios. So I just have this output file called Monroe storage %. It represents the combined storage of the 3 reservoirs that comprise Monroe's system. Down here, you notice, since I had selected different runs, I can choose to do all or not, or well, you need one, but I can choose to process both of these runs. And if I do that and press process, what it's doing is running this little post-processing script, and then it's going to appear in a plot window. And plot windows will show both the tabular output data here and then also a plot over here. I can take the plot and drag it so it's the full window if I'm just interested in that. And up top is, the full plot, and on the bottom is a scroll bar showing the results for the full period of record going back to 1930. Right now it's just showing like a 2-year slice of that. I can change this in a number of different ways. I can highlight this little pink box here and drag it if I want to look at more data. And you notice it just changes with me. Or if I'm in the plot here, if I have the plot highlighted and I go to scroll step, I could say I want to look at 10-year slices because that's a little more readable. And then you can drag across the historic record. So you can see, as expected, my test 1 scenario, which is where I increase the demand, draws down Monroe's reservoirs more than the default scenario. And I'll do a little more with post-processing later, but that's just to give you an idea of how you can start to quickly screen scenarios that you have created. I'm just going to close that. And close that. Okay. So that's, I mentioned we have a number of tutorials. That was kind of the introductory tutorial that we'll have going, that we'll have up on the server. I'm going to close everything and start the next tutorial is how to look at different types of input data in the model. Generally, a model consists of 3 main types of input data. There's time series data. So that's things like the inflows coming into the model, and the net evaporation is a time series in these models. There's the operations control language input. So that's, as we've mentioned a couple of times, the code that we use to represent more complex operations in the system. And then there's what we call static data. So that's things like the tables of stage storage area curves. It's things like repeating patterns, lookup tables, things like that. So if I go back to my Find Runs tab, and let's just search, we could search for Symbase again, but I could just pull up Symbase here. If I search by my name, you notice here you can search by date, which can be useful. And then instead of opening the schematic, I can actually just start to look for data in this run right from here. So let's say I wanted to look at the inflow time series for a certain node. I can click on this Find Data in Run button. That's going to open a new window. And so all it populates by default is say, I want to look for data in this specific run. So you notice I have some different options there. I click the plus sign, and then I can start to search for a specific type of data. In this case, I want to look for data called OCL time series. OCL time series is going to be, again, that time series input data. So inflows and net evaporation. And if I just do that in search, it's going to give me a list of all the time series data in the model. Along with the documentation is going to be a list of all the nodes and everything. So if, obviously you're not going to have these nodes memorized. I don't even, well, I have a few of them memorized, but most of them I don't. You could also, have the schematic open side by side here. So that might be a useful thing to do. So if I open my schematic, that just takes a minute to initially load. And then I drag my schematic over to the right here. And then let's see, if let's say I'm interested in, I go back to my Find Data tab. I say, okay, there's how many inflows? There's 3 inflows upstream and including Karscott Reservoir. It's inflow 4, which is this Yadkin River at Patterson gauge. Node 14, which is Elk Creek gauge. And then we have the remaining incremental inflow down to Karscott, which is node 10. And so something I could do is I could highlight those 3 time series here. And then in my input data tab that's open, I could click plot window. Okay. And what that is going to do is I'm going to maybe move my schematic back over here and then go back to that plot window. So what all that did is it opened up those 3 time series. And again, by default, it opens up the tabular data. So I could take this data and copy it to a spreadsheet if I wanted. And then it also shows it plotted here. So I can just kind of see what it looks like as a plot. And then I can do the same sort of thing here. I can zoom in, all that fun stuff. Then I can scroll. So that's a quick way to access some input data. I'll also show we have a number of pre-made output processing files that makes it a little easier to look at if you're interested in looking at like all the inflows or all the demands or something. We have some files set up to be able to do that. But this part of the demo is just more geared towards if you're interested in looking at a couple pieces of input or output in a specific part of the system. All right. So next, so that's time series data. And then there's also evap data that's going to be as well. The ones with the funny names there, don't worry about those right now. Those are a bit for forecasts. Oh, you know what? Sorry, for finding evap, there's actually a specific tag for that. So that's why that didn't show up. So if I went back to find data and run, and then type is reservoir evaporation, has its own little data category. So here's my evaporation for each node. So here's node 10 is Scott. Open that in a plot window. That's going to show my net evaporation time series for the entire period of record. Net evaporation, if anybody's not familiar, it's evaporation minus precipitation. So when you see a negative value, that means there's a rainfall event, and then the smaller positive repeating values is our net evaporation pattern that we're using in the model, or evaporation pattern in the model. And the units are inches, and what the model does is multiply the depth of net evaporation essentially by the surface area of the reservoir on a given day, and calculates the volume of net evaporation for the mass balance. And you can actually view that right from the schematic as well. I'm going to search for a different type of data here. Well, not search, I'm just going to open up what's called, so if I have a run selected, back to my run tab, you can open up what's called main OCL, and the little drop down will say this is the main OCL file. And what main OCL is kind of the starting point for the model. So what the model does is essentially it reads through this in order. So it reads something called our UDEF list, where the model does use a number of user-defined variables for different things. Those are all set there. And then it goes through the actual OCL files in the model that dictate different operations. And you can see they're broken out by things like agricultural calculations. I'll talk about filter inflows in a sec, and then specific things like Scott has its own OCL file. The wastewater returns has their own OCL file. There's some miscellaneous operations. Main stem is going to refer to, the main stem hydropower ops. The LIP has its own OCL file. Routing for those couple time of travel nodes. And then as well, we have the water shortage response plans, or the drought plans. And, there's a lot of comments here. There's some post-solve stuff done on hydropower generation. So this is actually when the model's solving each time step, and it does some post-solve based on what happened. But let's click, for example, if I go to like main stem operations, and what I can do is double click from here. It'll open up that OCL file here. And you noticed for the first 100+ lines, it's all just green text. Green text in OCL means comments. So this is Steve's manifesto on the operations on the main stem, basically. And so, I mentioned we're going to have a or there's a full report that goes along with this model, but we also make sure to keep detailed comments in the code itself so that you don't necessarily have to refer back to a report when you're digging in the model. Essentially, you know, if an assumption came from a specific report or license or email, we would generally document it in the code. This is going to be the more complex one out of the whole model, just because there's so many assumptions that go into trying to approximate the operations. But one thing you notice, there's more comments than code actually. So as Steve mentioned, this is a approximation of hydropower ops on a daily basis. And I think in this case, and maybe Steve wants to chime in, you know, there's more, it's more important to kind of have the theory behind the assumptions than the actual code itself takes to write out in this case.
Yeah, I put down a lot of commentary because of the significant changes in the license conditions over the years. And these projects have a significant impact on flows in the main stem.
Sure. And then if I was, you know, double click on something like water shortage response plans, I have not as much comments, but it kind of explains, sets up what's going on. I've got the WSACC's water shortage response plan, and don't worry about trying to read the code right now, but I'm going to do some exercises that shows a little bit about how to do some OCL coding. One thing we leverage in OASIS is this idea of 4 next loops. So instead of having to write out, you know, multiple blocks of code for each of WSACC's 4 drought triggers, essentially what I do is loop through this, because their triggers all take the same form, essentially, in terms of, I believe they're all just based on reservoir drawdown. And so it just loops through trigger 1, 2, 3, 4. I have a specified demand reduction percentage at each trigger. And then it's essentially subbing those values into this code where you see these square brackets as it goes through the loops. So if someone wanted to come in and change the demand reduction percentages, they could quickly do that here, and it would propagate in the run really easily. And then actually for a lot of these plans, so WSACC's has some detail, their plan's a little more unique going on than maybe some of the other entities, but there's Albemarle, there's Denton, there's Norwood. I think we loop some of these, but so you can go through and look at everybody's drought plans. Car Scott's right here, I'm going to double click on. Again, we have a lot of reference to the water control manual and our assumptions on how we're, you know, we have a link there on how we're representing their operations, and we're essentially setting a min flow. And then we also have some setting of a max flow during flood conditions. So that's how that's set. And essentially the way this works is, I'm going to write some code later to kind of walk you through it, but OASIS uses, instead of if-thens, we typically use these condition value statements. So instead of having to do a bunch of if-then loops for every possible condition that might occur, I set a condition. So I'm saying if the reservoir is less than 1023, min flows this, and then I kind of step up in the reservoir. And then eventually what you're going to do is hit a default condition. So default's essentially, if none of these conditions are met, this is what my default value is. So this is used a lot in the model, and it's a pretty efficient way of representing conditional operations. And then you notice also one thing that OASIS has is this convert units function. So the default unit in the model and in all of DWR's model are acre feet. I think that's primarily driven because there's always been, or in most models, there's been Corps of Engineers projects, and they go by acre feet. So we've always defaulted to that. So you just got to make sure if you're writing code in the model, if you're referring just to a number, you need to relate it to the base units. And so that's what we're doing here. let's see. The last thing that we can look at before I'm going to do an example of another alternative. You notice there's this wastewater returns OCL. So this is how we capture, it's got a little garbled, but the wastewater returns are defining all my wastewater treatment plant and also water treatment plant process returns in the model. And you notice we handle a lot of these in 4 next loops. And just kind of for efficiency, we're doing this loop for all the, these are all the linked wastewater treatment plant returns. So these are going to be all the wastewater discharges in the Yadkin and PD linked to a demand node. And so this is the node number in the 4 next loop. This is the name of the entity being looped. And then the ARC numbers, what we've actually done is embedded those in what we call a substitute list. So I have the substitute list called link WWTP return ARC Yadkin PD. And you see here, see UDEF list for the ARC numbers. If I go to my UDEF list, which is right here, I'm defining maybe some user-defined variables. Those are usually preceded by a underscore there, just to know that it's not like a built-in variable. It's something that we created for this model. But near the end here, I have all these substitute lists. And what these are is, if I define this list as a group with comma separated values, these are essentially all the different ARC numbers that are associated with wastewater treatment plant nodes linked to a demand node. So that way I don't have to go and type them all out individually in this OCL file. I have the list here, it automatically gets read in here. And so the nice thing about that is, let's say you add a new demand node that has a new wastewater treatment plant discharge, or you add a new treatment plant discharge. Let's say an entity builds a new wastewater treatment plant and it discharges to a different location than their existing one. All you would have to do is change the ARC reference number here, and it's going to propagate wherever it's called later on in the model. So you only have to change things one place, and you don't have to go searching for it. It's going to be in one place. And what it does is it's going to say the flow in that ARC that I just showed has to be equal to a pattern or a lookup table that defines how much wastewater they're discharging times the delivery to the demand node for that month. Okay. So much like how we have a monthly pattern for demand, we also have a monthly fraction for wastewater discharges. And again, that's based on that same most recent 5 years of data, where we take a look at how much wastewater is being reported discharged and divide it by the volume of demand being delivered. And that gives us our wastewater fraction for each month on an average basis. And so one thing I could do is, if I want to go and look at these lookup patterns, if I go back to my Find Runs tab, if I go to my Find Data and Run, I'm looking just in Symbase in this case again. I click my little plus sign. And this time I want to look for OCL lookup. So all the wastewater return patterns are stored as OCL lookups. And I click search, and you notice I think there are some other lookups for things like spill on some of the projects and stuff, but for the most part, we're using OCL lookups for these wastewater return patterns. So if I clicked on just like North Wilkesboro, for example, and clicked plot, this is the wastewater return pattern. So it's a little different than the demand pattern I showed you. A lookup always has an independent and a dependent. The independent in this case is the month, so 1 through 12. The dependent is the fraction of wastewater being returned as demand, or the fraction of demand being returned as wastewater for that given month. So, and generally it's kind of the inverse pattern of demands. the fraction of wastewater being returned is higher in the winter, lower in the summer, and that's because systems had more outdoor use in the summer, so less percentage of their water is being put into their wastewater collection system in the summer as a percentage, since a higher percentage their full demand is outdoor use. And then if I go back to my wastewater code, I just refer to that in the code as lookup, and then the name of the lookup pattern there. And then after the comma is the independent value, where in this case I had mentioned it was month. So that's going to give me a value of whatever the fraction is. So if my demand was 10, or if my delivery was 10 for the month and my wastewater return fraction was 50% for the month, it would put 5 MGD through that arc. So that's how that works.
And this will automatically factor in any demand restrictions. If we turn on the water storage response plans,
yep,
demand gets reduced, wastewater return gets reduced.
Yeah, that's the nice part about coding it this way. We link as many wastewater discharges to the demands as we can, because that way, if you increase demands in a planning scenario, the wastewater is automatically going to increase by the same fraction. And then, like Steve said, if you're running the model with the wastewater, with the drought plans turned on, and let's say demand gets cut back by 25%, it's going to also cut back the wastewater return proportionally.
And
right?
the last thing on that, those 4 next loops are super useful, in
Yep.
part because we can track, for instance, the summation of withdrawals and discharges by sub-basin. So again, for consistency, we're matching up with HDR's planning document, future projections document, which is broken out by sub-basin, one for Karska, one for High Rock, one for Tuckertown, so on and so forth. And in the UDEF list at the end of it, that's where I aggregated all of those demands and discharges.
Yeah.
So that we can do a quick comparison.
Mm-hmm. And let me just show those quick, actually, because those will all be included with the model as delivered. If I have the run open anywhere, I can click this process text button. So I've shown process plot today. Anything you can process as a plot, you can also process just as text output. And actually, you can do more with text output, because let's say we have a number of like large system all files that essentially, like for the LIP, we've put all the variables that go into calculating the LIP and viewing it into one post-processing script, and that way you can quickly pull that up and look at everything going into it and debug it, or look at the dynamics of why it's turning on or off, that sort of thing. But like Steve mentioned, we have a number of post-processor codes tied to those 4 next loops of different groups of outputs. So let's say I want to look at all of my wastewater returns that are linked to demand nodes. So that's essentially that substitute I just showed right there. So I can pull that up, and we also have a monthly version, just maybe a little cleaner to read. So if I do that, it's just processing those.